everyone, this is Nina and Meryl, and we're going to present the physics of noise cancelling, mastering sound waves, as our Physics 23 final project.
Noise-canceling headphones have been on the rise for years. Whether you're studying, working, or just listening to music, you'd want to maximize your ability to hear by canceling out noise from your environment. We're going to analyze how noise-canceling headphones function using physics. Before we dive into noise cancelling, let me first explain some background knowledge to help everyone understand it better.
So, what is a wave? A wave is a disturbance or vibration in particles that carries energy from one place to another without moving the matter itself. There are three key properties to remember when we talk about waves. One is amplitude. This is how high or strong the wave is. It shows the energy of the wave. 2. Wavelength. This is the distance between two wave crests or peaks. It tells us how long one full wave cycle is. 3. Frequency. This tells us how many waves pass a point in a certain amount of time. As shown in the diagram, the wave has crests and troughs. The wave moves energy forward, but the particles themselves just vibrate in place. This is how energy travels to waves in different forms like sound, light, or water.
What is sound? Sound is a type of mechanical wave, which means it moves by making particles in a medium like air, water, or solid vibrate. This vibration travels through the medium as waves. For example, when an object vibrates, it pushes and pulls the surrounding particles. This movement is what allows sound to travel our ears. However, since sound depends on a medium to propagate, it cannot travel through space, like in a vacuum.
One way a sound wave can be quantitatively described using the formula V is equal to F lambda, where V is the speed of sound, F is the frequency, and lambda represents wavelength.
Now, let's start talking about noise cancelling. Noise cancelling refers to the process of reducing unwanted ambient sound, allowing users to focus on their music, calls, or quiet moments. There are two main types of noise cancelling, which are active noise cancelling and passive noise cancelling.
Start with the active noise cancellation. It relies on electronics to generate sound waves to cancel out the unwanted noise. It uses built-in microphones to detect and analyze noises surrounding you and then generate an opposing sound wave to cancel out the unwanted noise. This is most efficient on low-frequency noises such as sounds of airplane engines, refrigerator hums, lawnmowers, and etc. Essentially, this is an example of destructive interference in our everyday world, which we will explain later.
Passive noise cancellation relies on the physical design of the headphones to cancel noise. So this can be applied to over-the-head headset where the cushioned earpieces fully cover the ear, insulating your eardrums to the tight-fit headset. This type of headphones is most efficient in high-frequency noise such as a child crying and sirens.
Cancellation can be used anywhere you want, but people most often use this feature when traveling in urban environments, studying, working, or exercising to drown out the unwanted sounds and to maximize your ability to hear music for concentration purposes.
So far, we talked about noise cancellation, so what are the physics applications of noise cancellation? The interference from physics allows us to explain noise cancellation. Interference is a phenomenon that occurs when two waves meet while traveling through a medium and overlap in the same space. The outcome depends on the principle of superposition, which says that the resulting wave is simply the sum of the individual waves' amplitudes at each point. This interaction creates two key types of interference, constructive and destructive. Before comparing constructive and destructive interference, let's first look at the interference of sound waves.
We can explain the concept of sound wave interference using this mathematical formula. This formula describes the resulting wave of the interference of waves. First, A2 cosine phi over 2 represents the amplitude or loudness of new wave, which depends on the phase difference phi between the two original waves. Second, Sine kx minus omega t plus phi over 2 describes the shape and motion of the resulting wave, including its frequency and phase. The phase difference phi is crucial in determining the type of interference. When the phase difference is small, the wave combined constructively, creating a louder sound. When the phase difference is large, the wave can cancel each other out, causing a destructive interference and reducing or silencing the sound. This formula explains how the characteristics of the two original waves influence the final sound wave.
A constructive wave is when two waves of the same frequency line up and produce a larger amplitude of sound. Observe the wave simulation. F of xt is the starting wave, and when a wave is with a large amplitude gxt is added, the final wave u of xt is the result of the added waves.
Destructive wave is the opposite of constructive interference. A destructive interference is when two waves overlap each other in a way that they can cancel each other out, and that causes a noticeable decrease in sound volume. As you can see from the wave simulation, when f of xt has amplitude of 2 and when u of xt has amplitude of -2, when they are added together, they create a flat line, meaning the two waves cancel each other out and therefore no sound.
Well, how does noise cancelling work? This slide explains that noise cancelling uses the principle of destructive interference to function. Noise cancelling headphones produce sound waves that are the exact opposite or inverted version of the ambient noise around you. When these two sound waves, the noise and the inverted wave from the headphones, overlapped, they canceled each other out through a process called destructive interference. As a result, the unwanted noise disappears. In this way, noise-canceling headphones create a quieter listening environment, allowing you to focus on the sound you want to hear.
The quality of sound is closely related to how noise-canceling technology works. The formula for sound intensity is I is equal to delta P max squared over 2 rho V. I is the sound intensity and represents how loud a sound is. Delta P max is the maximum pressure variation caused by the sound wave. Rho is the density of the medium through which the sound travels, and V is the speed of sound in the medium. Sound intensity helps us understand the energy in sound waves, which is key for technologies like noise cancelling.
Decibels are a unit used to measure the intensity of sound, representing the ratio between a given sound intensity and reference level on a logarithmic scale. In this formula, L represents the sound level, and I is the intensity of the sound being measured, and I0 is the reference intensity. This calculation uses a logarithmic scale, which simplifies the comparison of sound intensity, especially when the differences are very large. Using decibels, it is also possible to measure the effectiveness of noise-canceling technology by determining how much the sound level is reduced compared to the original noise intensity.
So with everything in mind, let's compare noise-canceling capabilities in AirPods Pro versus the Bose headphones.
AirPods Pro uses active noise cancelling, and the active noise cancelling reduces noise by 27 decibel.
To the AirPods Pros, Bose Soundtrue around-ear headphones use passive noise cancelling, so there is no electronic technologies producing opposing sound waves. This model is able to block out noise due to its materials used and its ability to insulate the ears. Explain noise-canceling phenomena using physics of waves. In conclusion, we covered topics like waves, sound waves, interference waves, and the physics of noise-canceling headphones. Thank you for listening.